Circuit breakers allow the flow of energy to be controlled by safely switching currents on and off at all voltage levels of the energy grid. In the open position, they have to ensure isolation across the switching distance, between phases, and to ground. In the closed position, they have to allow the energy to flow with minimum losses. They need to be able to reliably interrupt short-circuit currents without damaging themselves or adjacent equipment, even after long idling times. Different circuit breaker technologies are in use, depending on voltage level, application, and the age of their design. Current interruption takes place in interrupter chambers containing air, oil, SF6, or a vacuum. Circuit breakers may use multiple contact systems consisting of main contacts and arcing contacts. The main contacts allow operating current to flow with minimal losses, while arcing contacts can break short-circuit currents with minimal arcing erosion. The braking element is usually operated mechanically by a stored energy system. The energy that opens and closes the contacts is typically stored in a spring, hydraulic, or pneumatic device or system. The stored energy is released by the trip or the close command signal. The command signal activates the trip and close coils, releasing the drive mechanism to perform the opening and closing operation. The interrupter and the mechanical drive are the main components that are subject to wear and aging. The thermal stress of load currents may cause corrosion and oxidation, and the interruption of short-circuit currents erodes the contact system. Environmental stresses, such as temperature, humidity, or contamination, affect the bearing and linkage surfaces of the drive. Ancillary components, such as bushings, are also subject to electrical stress aging. In order to ensure the proper operation of a circuit breaker throughout its lifetime, diagnostic tests are performed, such as resistance, timing, minimum pickup, travel, and power factor. In order to achieve the best safety conditions for the test engineer, the circuit breaker should be grounded on both sides during most of these tests. The first test usually performed on a circuit breaker is the static contact resistance in the closed position. The static contact resistance is determined by injecting a high DC current while the voltage is measured via a separate set of cables. An analysis of the opening and closing times of the circuit breaker contacts can validate mechanical performance. Differences between individual contacts and individual phases must fall within defined limits. Comparing these results to factory data or earlier measurements can reveal trends. Recording trip and close coil currents gives an indication of their mechanical and electrical condition, as well as the condition of the latch. The minimum voltage, known as minimum pickup, needed to trip and close the circuit breaker is also usually measured to ensure that it can still operate in case the DC supply is weak. If the breaker is equipped with a multiple contact system, measuring the dynamic resistance during opening and closing will indicate the wear of the arcing contact. Additionally, if the circuit breaker travel curve is recorded, it allows mechanical parameters to be assessed, such as velocity, total travel, acceleration, over travel, and rebound. By performing these measurements, the station operator can verify that the equipment is in good working condition or can initiate maintenance activities.